Hello, welcome to EET3085 lab session. In this lab, we're going to be looking into the response of the RC circuit to a square wave. So RC circuit simply a circuit like this one with a resistance and capacitor. So we know that the equation for the value of the voltage here in the capacitor is given by this equation. Very important term here is the tau here, is the time constant, which is equals to the product of the value of the resistance and the capacitor. Is a time constant gives us an idea on how the behavior of the circuit is for the time, how basically the capacitor charges and discharges compared to the timing given in the input. Okay, so for instance, we can assume that if we have a square wave like this, in which we are given a period, by the way, a period is a time for in which the pattern is repeated. So see that we have a pattern here with up pulse and then a zero that follow that. They're supposed to be equally timed, the same duration, each one, the pulse and the zero. Usually in this case we call a duty cycle of 50%. So 50% the pulse remains high, 50% of the cycle remains low. Okay, and then we assume that half of this period, of the t, is going to be tau. So we use that particular value of RC equals that. So for that, if we plug the values of the tau in this equation, then we're going to see that the voltage in the capacitor is going to be 0.633 times the peak here of the value. That will be for the first pulse. Okay, so it's like 63% of the value. See that we're not plugging any particular value here, but in general, what is the percentage here for the particular tau with respect to the cycle. Okay. Okay. So what happens is if we have taus, or we select pulses, size of the pulses with t or the period very long, then we're going to, for instance, in this case, half of the period, t1 is 5 times tau. Then we see that the capacitor reaches the top almost charged. So because once the capacitor is charged, it's going to give us sort of a flat response to the voltage here, the final voltage here. We have this table that can help you to see also the relationship between the timing of the pulses that we're using, okay, with respect to the tau. So for instance, we T1 or half of the cycle is equals 1 tau, then we have seen that we only reach 63% of this signal. If we have instead 2 times tau, so double the time, then we reach 0.865 VP. So it's like at 86% of the maximum voltage. Whereas when we reach 5 taus, then we assume that we have almost full charge, the capacitor, which is 0.994 the voltage of the peak in the input. So the main idea with this lab is to do this using multi-sim. So we want to have a form that we can generate using a waveform generator, this available in multi-sim, and we're gonna use R and C circuits, and we're gonna use a multi-channel oscilloscope. I know that some of you have not had exposure with the oscilloscope, we have in the, if you allow me, in the manual for the multisim, if you look into chapter 9, we have almost all the instruments explained there. And one of the one that we have is the plain oscilloscope. We have several there, and I may show you exactly what and how the oscilloscope work. So remember, the idea with the oscilloscope is that we are able to see the signal changing in time. So for instance, in this case, we have two signals. I don't know if we were able to see that. Let me give a bit more of put it a little bit bigger. So see that we have two signals. One is a sinusoid in red, and the other one is a shape that is something that resembles a bit of a sinusoid, but with the top peaks sort of clipped there. So see, we have two channels. One channel allows me to see this signal that's coming from a particular point that I'm testing. The other one comes from a different part of the circuit. One would be the source, and the other one, for instance, in our case, the voltage in the capacitor. So see that essentially we have three things that we need to control there. One is the amplitudes of each one of the signals. So we have the peak-to-peak amplitude that we can select here in the channel A and channel B. And then we have a scale. That scale you select according to the maximum of the wave that's going to be shown there. So for instance, if you have a wave that goes 10 volts peak to peak, then you should select the size here accordingly to be able to show the whole wave. So one of the things you have, let me give you some of the oscilloscope from the book. By the way, the book in chapter 13 has some insight about the oscilloscope. This is a real-life oscilloscope, and this is pretty much what I'm trying to explain to you. This is a simple signal. It's a sinusoid. So see that we're looking into the time, how this signal changes in time. That's why we cannot understand, or we cannot analyze any circuit in AC alternating current if we don't have an oscilloscope or something that allows us to see how the signal behaves in time. In this case, we have two. One thing is very important. Normally, we associate you see that the screen here of the oscilloscope is a grid, and the grid has small squares. Those are the divisions. So if you want to read a value here, you need to read how many divisions. For instance, in this case, we have a sinusoid, and then we have one division from here, 2 division, 3, and 4. So the peak-to-peak value is going to be 4 divisions. And then you go into the scale that you set in the oscilloscope. In this case, the vertical sensitivity is going to be 0.1 volt per division. Therefore, you have 0.1 volt here, plus another 0.1, plus another 0.1, plus another 0.1. So we have 0.4 volts in total. Similarly, the time. You see, we have a time we have the sensitivity of the time. In this case, for instance, the whole period that we're talking about, the whole time that the wave takes to repeat the pattern. So we start here going up, and then we get the complete point in which we have the maximum of the wave. Then we go back, reach the minimum or the negative part of the wave, and they go back to 0. So see that we start at 0, and then we go here into 0, and then we repeat the same cycle. From here up to here is what? Is the period of this wave. In this case, we have a sensitivity of 50 microseconds per division. So what would be the period? So we have 1 division, 2 division, 3 division, and 4 division times 50 microseconds, so we have 200 microseconds. Okay, so having said that, then we have some ideas on how we're gonna be doing this. The other thing is the how do we are going to generate this waveform. Initially, there's an explanation here you can read. Of course, you're supposed to read this, that this is what we are trying to emulate, closing and opening the switch here to produce pulses. But we have an equipment that is able to do that, which is the waveform generator, right? So we have a waveform generator, also part of the set of instruments that we have available in the multi-sim, and then we're going to be looking in the scope. So this is a very simple circuit that we set from the waveform generator into the scope directly to there. So remember, we're saying that in our oscilloscope we have more than one channel. Okay, let me bring back the multi-sim oscilloscope, and see that we have this is the time control, the sensitivity for the timing, and this is the one for the channel A and the channel B. All right, then we have some other controls that we want to be setting there. Okay, so initially we would like to build, well, not exactly this circuit, you can do it, but I'm gonna go further. I'm gonna show you pretty much this circuit. That's the one that we use to to do the practice, this lab in the lab. In this case, we have the wave generator here. If this is a very simple wave generator in which the polarity goes from 0 to the maximum, then, well, you see that we're not interested in that, or because we want to start the pulses from 0. See, this is 0, so we want to check what happens if I go to 0, from 0 to the top, not from minus to the top. That will give us a different reading. Therefore, if we're using, for instance, in this case, a 6 volts peak to peak, and then we put this in series, a 3 volts power source, see that we're going to start then subtracting from 0 the 3 volts. In other words, here's the thing, we're going to start from 0 up to 6 volts. Why? Because this is an offset. This provides an offset, constant offset of 3 volts. So if I start with 0 here, then it's going to be 3 volts. If I go to 6 volts, it's going to be 3 volts. If I'm going to have here minus 6 volts, it's going to be 0. Okay, so always an offset. So we can do, there are some equipments, wave generators, that have the offset. And one of the one of you using here is that, but I'm going to plug exactly the same circuit as it is depicted here. Okay, so this circuit, we have a square wave generator, which we are using at 10 plus minus 10 volts. In the, by the way, in the Word document, okay, we're supposed to use plus minus 6 volts. Okay, 6 volts plus 3 with the offset. In this case, we use the wave generator with the offset included. All right. So, but I'm gonna show you how. I mean, if you rather use the power source externally without the offset, that's fine. So we want to build this circuit, okay? And then we want to do some examples with that. So let's go to the multi-sim. Okay, so this is the circuit. You can get the oscilloscope from here, right? This is the oscilloscope. If you click that, then you get this exactly, okay? There's some other kind of oscilloscope here, more sophisticated. Let me see where we have one that is multimeter. This, okay. See, this is much more sophisticated. It's like just a real type of oscilloscope, and then you can turn it off and then and on, and then use the channels and you know, set according to what you need. But let's keep this for later. We don't delete this. Okay. So we're gonna be using this oscilloscope. If you double click here, it's pretty simple. This is what I meant. I already got this from before. I'm gonna show you how we get that, so don't worry. So we have here the time scale or the time sensitivity, and then we have each one of the channels. You can adjust that up and down. All right. Similar with this. Okay, you can use less, more, or whatever you want. And similar with the time. Okay, so you want less resolution or more resolution of the time. It simply expands. See that you have 2 milliseconds per division. So between these two in the grid, between these two vertical lines in the grid, you have 2 milliseconds. So it's easy for you to find what's the time between this and this. Okay, so you can use segments here of the divisions. It's not that difficult. All right, so this is the oscilloscope, and this is the waveform generator. So waveform generator gives you these possible values, or you can adjust the frequency. You start with 160 hertz. You can use 150, and then the duty cycle is 50. So meaning that 50% is up, 50% is down, and the amplitude is 10 volts peak to peak, and not offset. See, I could use offset of 5 volts as there, and then it's just exactly like the graph that we have there without the offset. Okay, so this is our waveform generator, and this is our oscilloscope. So if we run that, this is the circuit. Remember, we have the oscilloscope has to be connected, the common to ground, and then you have 2 channels. You have the channel A and the channel B. This, in this case, if you look into no, it's not this, I'm sorry. In case of the lab, okay, we have then the square wave generator. The plus goes to the minus of the source, the 5 volt source. Then we go to the scope. One of the scope, the channel A will be here between ground and here. Then I have the resistance, and then the capacitance, and then the output of the capacitor is going to be checked from here. Okay, from between B and ground. Okay, back to the multi-sim. If you look at this is exactly the circuit that we're checking. Channel A goes into what is the point A here before the resistance, and the channel B here in after the resistance between the capacitor. And I'm using only one ground. We need the ground there. Similarly with the waveform generator. So this is basically what we need to use. So we start running. Then you can have a single shot here. See that we have DC, DC, and DC here, because I want to see the offset. Okay. In this case, I'm using, if the signal is going to be AC starting in 0, that's what we have. Okay, we have a problem. I haven't been able to see what is going on with this, but this is the 0. This is supposed to start with 0 because we have 10 volts. Okay, and certainly if we are doing 10 volts here, you can see that we go from 0 to 10 volts. It's like if I add some offsets, not to the source, but to the scale, to the measurement equipment, then you see that we have 2 divisions here, and each division is 10 volts. Therefore, I have 20 volts peak to peak, or 20 volts between this and this. 10 volts are given by this, right? Or we can actually use 5 volts. That's also possible to see that more. Let's stop that, and then we have 5 volts here. Okay, so the voltage should be just like that, no offset. So now see what happens. We start then, if you look into what's going on with the capacitance, see that the frequency is too low. That means that this waveform, the flat here, remains for a while longer than the time. Now, if you start then modifying the frequency, right? You see what's going to happen. For instance, we have 500 hertz. Let me see if we can change that. And normal. Okay. Now you see that the situation changes. We need to adjust this. So see that now we see that we still have a rising and then some flat. That means that the capacitor is completely charged here, right? But let's go into a 1 kilohertz. You can hear 1 kilohertz. Okay. Okay, let me see. We need to rerun that. Okay. All right. So this is 1 kilohertz. See that now, as expected, you have to figure out. You have to use the equations to find actually the percentage of charging of the capacitor here. The point is that if you change this, if you change these frequencies, then you're going to have a much better view. Let me, if I can put them together just like that, okay? And yeah, so that gives you a much better idea on how they behave. Okay, so and you keep adding more and more frequency, then you're going to notice that, for instance, I see 5 kilohertz, right? Let's see and rerun that 5 kilohertz. I'm using single. Single means that it's only one sweep, okay? And we need to use more of that, okay? Which is similar. We're expecting now to see less and less of charging of the capacitor because this is faster and faster and faster. So this is pretty much what we have here, this depicted in this situation. Okay, over here. It doesn't charge completely, doesn't discharge completely. Okay, I think that that gives us a very good idea on how to work with these. You have this, by the way, you can calculate exactly the size. See that if I move this cursor to number 2, this number over here will change. Okay, so that allows you to use them. All right. In this case, this is for the, see the point here. This is for this wave, and the other one is for the other channel as well. Okay. So you can figure exactly what the amount is. Okay, I hope that this works. You let me know if you have any questions, and well, thank you so much.